Imagine waking up every single day for your entire life to the sound of rain. Now imagine your children doing the same, and their children, and their children's children. For 67,000 generations, not a single day passed without rain falling somewhere on Earth. This wasn't just a bad weather streak. This was the Carnian Pluvial episode, when our planet turned into a water world for 2 million years straight, and it changed the course of life forever. While most creatures struggled to survive in this endless deluge, one group of small, unremarkable animals saw their greatest opportunity. These were the early dinosaurs, and they were about to inherit the Earth. To truly grasp the magnitude of what happened during the Carnian Pluvial episode, we must first step into a world so alien, so fundamentally different from our own, that it challenges everything we think we know about Earth. This is the story of our planet 237 million years ago, during the Middle Triassic period, when the stage was being set for one of the most dramatic climate transformations in geological history. Picture a world without a single blade of grass. No flowers have ever bloomed on this ancient Earth, because flowering plants are still tens of millions of years away from evolving. There are no ice sheets gleaming white at the poles, no snow-capped mountain ranges, no frozen tundra stretching to the horizon. Instead, our planet resembles a massive greenhouse, where temperatures soar to levels that would be lethal to most modern life forms. The global average temperature hovers around 35 degrees Celsius. That's nearly 20 degrees warmer than today's climate. In the interior regions of the supercontinent, summer temperatures regularly exceed 50 degrees Celsius, creating vast expanses of desert that stretch beyond the horizon. This is the world of Pangaea, the ultimate supercontinent. Imagine every landmass on Earth today crushed together into one colossal mass, surrounded by a single endless ocean called Panthalassa. The sheer size of Pangaea creates its own climate nightmare. The interior regions, thousands of kilometers from any ocean, become scorching deserts where rainfall is almost non-existent. Only the coastal areas receive enough moisture to sustain life, creating a ring of habitability around the edges of this continental monster. But even in this harsh environment, life persists with remarkable tenacity. Massive forests of conifers, ferns, and cycads dominate the landscape wherever water can be found. These aren't the delicate ferns you might find in a modern garden. These are towering tree ferns that stretch 30 meters into the sky, creating dense, prehistoric jungles. Cycads, those palm-like plants that look almost tropical, grow in vast groves, their thick trunks and feathery fronds creating an otherworldly landscape that seems more suited to an alien planet than Earth. The animal life of this period tells its own fascinating story of adaptation and survival. In the shadows of these ancient forests, early archosaurs, the group that would eventually give rise to crocodiles, pterosaurs, and dinosaurs, are establishing their dominance. These aren't the crocodiles we know today, but massive terrestrial predators that walk upright on powerful legs. Some, like Prestosuchus, grow to lengths of 7 meters, their massive jaws capable of crushing bone. They are the undisputed rulers of this Triassic world, the apex predators that control entire ecosystems. And then there are the early dinosaurs, small, unremarkable creatures that most paleontologists of the time would have dismissed as evolutionary side notes. Species like Eoraptor and Herrerasaurus scurry through the underbrush, rarely growing larger than a medium-sized dog. They are fast, agile, and intelligent. But in this world, dominated by giant archosaurs, they seem destined to remain minor players in the grand drama of evolution. Little do these early dinosaurs know that they are on the verge of inheriting the Earth, thanks to an event that will reshape the entire planet. The climate of this Triassic world operates on principles that seem almost alien to us today. Without polar ice caps to regulate global temperatures, the planet's climate system is fundamentally different. Ocean currents flow in patterns we can barely imagine, driven by the configuration of a single massive ocean surrounding a single massive continent. The lack of significant mountain ranges in the interior of Pangaea means that weather patterns are dominated by vast continental-scale atmospheric circulation systems that create the extreme aridity we see in the fossil record. Carbon dioxide levels during this time are estimated to be 3 to 5 times higher than today's pre-industrial levels. This isn't just a number on a chart. It represents a fundamentally different atmospheric composition that drives the greenhouse conditions we see preserved in ancient rocks. The excess CO2 doesn't just warm the planet. It also affects the very chemistry of the oceans, making them more acidic and fundamentally altering marine ecosystems. The plant life of this period reflects these extreme conditions in fascinating ways. Many Triassic plants show adaptations to intense heat and drought that we rarely see in modern ecosystems. Thick, waxy cuticles protect leaves from water loss. Specialized root systems extend deep into the ground, searching for any available moisture. Some plants develop the ability to shut down their metabolism during the hottest parts of the day, essentially going dormant to survive the crushing heat. Marine ecosystems tell their own story of adaptation to this greenhouse world. The oceans are warm from pole to pole, with surface temperatures in tropical regions approaching 40 degrees Celsius, hot enough to kill most modern marine life. Yet ancient ecosystems thrive in these conditions. Massive reefs built by extinct organisms stretch across shallow seas, while in the deeper waters, entirely different communities of creatures evolved to handle the warm, acidic conditions. The geological evidence for these conditions is written in rocks around the world. Red sandstones and mudstones, the signature of hot, arid climates, dominate Triassic rock formations. Salt deposits and gypsum beds tell stories of shallow seas that repeatedly evaporated under the intense heat. Even the shapes of ancient river channels, preserved in stone, reveal a world where seasonal flooding was followed by months or years of drought. But perhaps most remarkably, this seemingly stable, if extreme world was balanced on a knife's edge. Deep beneath the Earth's surface, massive volcanic systems were building pressure. The same geological forces that had assembled Pangaea were beginning to tear it apart, and this tectonic activity was about to trigger a chain of events that would fundamentally transform the planet. The volcanic province, known as Wrangellia, stretching across what is now Alaska and western Canada, was growing restless. These weren't ordinary volcanoes, but massive flood basalt systems capable of erupting millions of cubic kilometers of lava and releasing colossal amounts of gases into the atmosphere. The stage was being set for an environmental catastrophe that would make the extreme conditions of the Triassic seem mild by comparison. As we stand at this moment in Earth's history, 237 million years ago, we can almost sense the tension in the air. The climate system, already pushed to its limits, was about to be subjected to the ultimate test. The small dinosaurs scurrying through the undergrowth had no way of knowing that their world was about to change forever, that the coming deluge would sweep away the old order and create opportunities beyond their wildest evolutionary dreams. This was the world before the rain, a planet of extremes, where life had adapted to conditions that would challenge our modern understanding of habitability. But it was also a world on the verge of transformation, where the stage was perfectly set for one of the most dramatic climate events in Earth's 4.6 billion year history. The Carnian Pluvial episode was about to begin, and nothing would ever be the same again. To understand why the Carnian Pluvial episode became such a transformative force, we must first comprehend the profound wound that Earth was still healing from, the greatest mass extinction in the planet's history. Just 14 million years before our rain-soaked story begins, life on Earth had faced its ultimate test of survival during an event so catastrophic that paleontologists simply call it the Great Dying. This wasn't merely another extinction event in Earth's long history of biological crises. This was evolutionary Armageddon, a near-complete reset of life on our planet that set the stage for everything that would follow. The numbers alone tell a story of unimaginable devastation. 96% of all marine species vanished forever. On land, the toll was equally horrific, with 70% of terrestrial vertebrate species disappearing into the fossil record, never to return. Entire ecosystems that had dominated Earth for millions of years were wiped clean, leaving behind empty ecological niches like abandoned cities after an apocalypse. The planet's biodiversity, built up over hundreds of millions of years of evolution, was reduced to a handful of hardy survivors clinging to existence in a world that had become fundamentally hostile to life. But what makes the Great Dying particularly relevant to our story is not just its destructive power, but the specific way it reshaped Earth's biological landscape. The extinction wasn't random. It followed patterns that would prove crucial to understanding why the coming rains would have such a dramatic impact on evolution. Large, specialized organisms were hit hardest, while small, adaptable creatures had the best chance of survival. Complex food webs collapsed, leaving simplified ecosystems dominated by a few generalist species. The old order of life, with its intricate relationships and specialized roles, was swept away, leaving behind a biological blank slate. In the marine realm, the destruction was particularly thorough. The vast reef systems that had dominated shallow seas for millions of years were completely eliminated. Ancient groups like the rugose and tabulate corals, which had been building reefs since the Ordovician period, vanished entirely. The trilobites, those iconic armored arthropods that had survived multiple previous mass extinctions over 270 million years, finally met their end. Brachiopods, which had been among the most diverse and abundant marine animals, were reduced to a handful of surviving lineages that would never again achieve their former dominance. On land, the devastation was equally complete, but followed different patterns. The great forests of the Permian, dominated by seed ferns and other ancient plant groups, withered and died. Massive herbivorous reptiles like the dicynodonts, some as large as modern rhinoceroses, saw their diversity crash from dozens of species to just a few survivors. The complex predator-prey relationships that had defined terrestrial ecosystems were shattered, leaving behind simplified communities where a few hardy species struggled to fill multiple ecological roles. The cause of this unprecedented catastrophe lay in the largest volcanic eruption in Earth's recorded history, the Siberian Traps. For nearly 2 million years, these massive flood basalts pumped enormous quantities of lava, ash, and toxic gases into the atmosphere. The scale of this eruption is almost impossible to comprehend. Enough lava to cover the entire United States in a layer 3 kilometers thick. But the lava was only part of the story. The real killer was the gases: carbon dioxide, sulfur dioxide, hydrogen sulfide, and other toxic compounds that turned the atmosphere into a poisonous soup and triggered runaway greenhouse warming. The environmental changes triggered by the Siberian traps created a cascade of disasters that compounded each other in horrific ways. The massive CO2 release caused global temperatures to soar by as much as 10 degrees Celsius, turning much of the planet into a scorching wasteland. The oceans became so acidic that shell-building organisms could no longer survive, while oxygen levels in seawater dropped to near zero in many regions, creating vast dead zones. On land, acid rain stripped vegetation from entire continents, while toxic gases made the very air unbreathable for many organisms. But perhaps most remarkably, this unprecedented catastrophe created the conditions that would make the Carnian Pluvial episode possible. The Great Dying didn't just eliminate species, it fundamentally altered the way Earth's climate system operated. The destruction of vast forests eliminated one of the planet's major carbon sinks, leaving atmospheric CO2 levels elevated for millions of years. The collapse of marine ecosystems disrupted ocean circulation patterns, creating instabilities in the climate system that would persist well into the Triassic. More importantly for our story, the Great Dying created evolutionary opportunities that would prove crucial when the Great Rains began. With so many ecological niches left empty, the surviving lineages found themselves in a world with unprecedented opportunities for evolutionary experimentation. Small, adaptable organisms that might have remained marginal in the complex ecosystems of the Permian suddenly found themselves free to explore new evolutionary pathways without competition from established giants. The recovery from the Great Dying was neither quick nor simple. For nearly 10 million years after the extinction, Earth's ecosystems remained impoverished and unstable. This period, known as the dead zone of the early Triassic, was characterized by simple communities dominated by disaster taxa, opportunistic species that could exploit the disrupted environment but lacked the diversity and complexity of pre-extinction ecosystems. Microbial mats, normally confined to extreme environments, spread across ocean floors and continental shelves, creating an almost Precambrian-like world in the aftermath of the disaster. During this prolonged recovery period, the survivors of the Great Dying were forced to evolve in an environment unlike anything their ancestors had experienced. The early archosaurs that would later dominate the Triassic evolved many of their key innovations during this time, developing the upright posture and advanced respiratory systems that would later make them such successful predators. Early dinosaurs, still small and inconspicuous, were nevertheless acquiring the fundamental adaptations: lightweight bones, advanced hip structures, and efficient metabolisms that would later prove crucial to their success. The plant life of the post-extinction world tells its own story of adaptation and innovation. The ancient seed ferns and other Permian plant groups were largely eliminated, making way for new lineages that were better adapted to the harsh, unstable conditions of the early Triassic. Conifers, with their drought-resistant needles and efficient water use strategies, began their rise to dominance. Ferns, always quick to colonize disturbed environments, diversified rapidly in the empty landscape. These plants were developing the characteristics that would later allow them to thrive during the waterlogged conditions of the Carnian Pluvial episode. By the time we reach the Middle Triassic, roughly 14 million years after the Great Dying, Earth's ecosystems had achieved a new stability, but it was a fundamentally different kind of stability than had existed before. The complex, mature ecosystems of the Permian had been replaced by simpler, more dynamic communities that were both more resilient to environmental change and more capable of rapid evolutionary innovation. This was the world that would face the coming rains, not the stable, established ecosystems of the pre-extinction world, but younger, more flexible communities that were still in the process of defining their ecological relationships. The Great Dying had essentially rewound Earth's evolutionary clock, creating conditions reminiscent of much earlier periods in the planet's history when major evolutionary innovations were more common. The survivors existed in a world with fewer constraints, fewer established relationships, and more opportunities for evolutionary experimentation. When the great volcanic eruptions that would trigger the Carnian Pluvial episode began, they would be acting on ecosystems that were already primed for dramatic change, already adapted to environmental instability, and already populated by organisms that had proven their ability to survive and adapt to extreme conditions. This was the legacy of the Great Dying. Not just death and destruction, but a fundamental reshaping of life's possibilities. The great rains that were about to begin would fall on a world that was still learning how to be stable again, still exploring the boundaries of what was evolutionarily possible, and still dominated by the descendants of the few, the hardy, and the adaptable. The stage was set not just for another environmental catastrophe, but for one of evolution's greatest success stories. Deep beneath the ancient seafloor of what would one day become the Pacific Northwest, something monstrous was stirring. For millions of years, the Earth's mantle had been building pressure like a cosmic pressure cooker, and now, 237 million years ago, that pressure was about to find its release in one of the most catastrophic volcanic episodes in our planet's history. This wasn't going to be a single mountain exploding in a spectacular but localized display of geological fury. This species Kogi was the birth of the Rangelia Large Igneous Province, a volcanic superstructure so vast and so violent that it would fundamentally alter the chemistry of Earth's atmosphere and trigger a climate catastrophe that would last for 2 million years. To truly comprehend the scale of what was about to unfold, we must abandon our human-scale understanding of volcanic eruptions. When we think of volcanoes, we picture Mount Vesuvius burying Pompeii, or Mount St. Helens blowing its top in a spectacular explosion that dominates news cycles for weeks. But the Rangelia eruptions belong to an entirely different category of geological violence, the flood basalts, or large igneous provinces that represent Earth's most extreme volcanic phenomena. These aren't mountain-building eruptions. They're world-changing events that reshape continents and rewrite the rules of atmospheric chemistry. The Rangelia province began its violent birth in what is now the deep Pacific Ocean, but its influence would spread far beyond its oceanic origins. Unlike the cone-shaped volcanoes we're familiar with, these eruptions emerged from massive fissures in the Earth's crust, cracks in the planet's skin that stretched for hundreds of kilometers and belched forth unimaginable quantities of molten rock. The lava didn't build mountains. Instead, it spread across the landscape like a fiery flood, creating vast plateaus of basalt that accumulated layer upon layer, ultimately reaching thicknesses of several kilometers. But the true destructive power of the Rangelia eruptions lay not in the lava itself, but in the gases that accompanied each massive outpouring of molten rock. Every cubic kilometer of lava that erupted carried with it enormous quantities of dissolved gases that had been trapped in the Earth's mantle for millions of years. As this lava reached the surface and began to cool, these gases were released into the atmosphere in concentrations that boggle the mind. Carbon dioxide poured forth in quantities measured not in tons or even kilotons, but in gigatons, billions of tons of CO2 that would fundamentally alter the composition of Earth's atmosphere. The carbon dioxide was just the beginning of this atmospheric assault. Sulfur dioxide erupted alongside the CO2 in equally staggering quantities, creating massive clouds of sulfuric acid aerosols that would spread throughout the global atmosphere. These aerosols had a complex and devastating effect on Earth's climate system. In the short term, they actually cooled the planet by reflecting sunlight back into space, creating what scientists call a volcanic winter. But this cooling effect was temporary, lasting only a few years until the aerosols settled out of the atmosphere. The CO2, however, would remain in the atmosphere for hundreds of thousands of years, trapping heat and driving global temperatures to unprecedented heights. The chemical violence didn't stop with carbon and sulfur compounds. The Rangelia eruptions also released massive quantities of hydrogen sulfide, creating an atmosphere that would have been toxic to most forms of life. Hydrogen chloride and hydrogen fluoride added their own deadly contributions to this atmospheric cocktail, while trace amounts of mercury and other heavy metals spread throughout the global environment. The very air became poisonous, forcing life to adapt or perish in the face of this chemical onslaught. What made the Rangelia eruptions particularly devastating was not just their scale, but their duration. This wasn't a single cataclysmic event that ended in days or weeks. The eruptions continued episodically for hundreds of thousands of years, with major eruptive phases separated by periods of relative quiet. Each new phase added more gases to an atmosphere that was already saturated with volcanic emissions, creating a cumulative effect that overwhelmed Earth's natural systems for absorbing and processing these compounds. The timing of these eruptions was particularly catastrophic for Earth's climate system. The planet was already in a greenhouse state, following the earlier Siberian Traps eruptions that had caused the Great Dying. Natural carbon sinks, forests, wetlands, and ocean organisms that normally absorbed excess CO2 were still recovering from that earlier catastrophe and operating at reduced capacity. When the Rangelia eruptions began pumping additional gigatons of CO2 into the atmosphere, there was simply no natural mechanism capable of absorbing it fast enough to prevent runaway greenhouse warming. The atmospheric chemistry changes triggered by these eruptions created a cascade of environmental effects that would ultimately lead to the Carnian Pluvial episode. The massive increase in atmospheric CO2 didn't just warm the planet, it fundamentally altered the way water moved through Earth's climate system. Higher temperatures meant that the atmosphere could hold vastly more water vapor, and water vapor is itself a potent greenhouse gas, creating a positive feedback loop that amplified the warming effect of the volcanic emissions. The warming triggered by the Rangelia eruptions was unlike anything in modern human experience. Global average temperatures rose by an estimated 7 to 10 degrees Celsius above pre-eruption levels, turning Earth into a sweltering greenhouse planet where ice was completely absent from both poles. But the warming wasn't uniform across the globe. The massive landmass of Pangaea created extreme continental effects, with interior regions experiencing temperature increases of 15 degrees Celsius or more. Summer temperatures in these regions regularly exceeded 60 degrees Celsius, creating conditions that were lethal to most forms of life. Perhaps most importantly for our story, these extreme temperatures fundamentally altered global atmospheric circulation patterns. The intense heating of the continental interior created massive low-pressure systems that drew moist air inland from the surrounding Panthalassa Ocean. The temperature differential between the scorching landmass and the relatively cooler oceans created powerful convection currents that would eventually drive the unprecedented rainfall of the Carnian Pluvial episode. The oceanic effects of the Rangelia eruptions were equally dramatic. The massive amounts of CO2 dissolving into seawater created widespread ocean acidification, making it difficult for shell-building organisms to survive. Ocean temperatures rose dramatically, with tropical sea surface temperatures reaching 40 degrees Celsius or higher. These hot oceans could hold enormous amounts of water vapor, creating the moisture reservoir that would eventually fall as the great rains. The eruptions also released massive amounts of nutrients into the oceans, triggering enormous algal blooms that further disrupted marine ecosystems. These blooms consumed vast quantities of oxygen, creating dead zones in the oceans that would persist for hundreds of thousands of years. The combination of high temperatures, acidification, and oxygen depletion created marine conditions that were hostile to most forms of life, further reducing the planet's capacity to absorb the excess carbon dioxide from the volcanic emissions. On land, the effects of the eruptions were equally catastrophic. The combination of extreme heat, acid rain, and toxic atmospheric gases created conditions that challenged the survival of terrestrial ecosystems. Many plant species simply couldn't survive in the new atmospheric conditions, leading to widespread forest die-offs that further reduced the planet's carbon-absorbing capacity. The surviving vegetation was forced to adapt to much higher CO2 concentrations, fundamentally altering plant physiology and ecosystem dynamics. The geological record of the Rangelia eruptions tells a story of unprecedented environmental violence. Layers of volcanic ash found in rocks around the world mark the major eruptive episodes, while changes in carbon isotope ratios record the massive CO2 releases. The chemical signatures of these eruptions can be found in marine sediments from across the globe, testament to the truly planetary scale of their environmental impact. As the eruptions continued phase after phase, year after year, century after century, Earth's climate system was pushed beyond any previously known limits. The atmospheric greenhouse gas concentrations reached levels that were 5 to 6 times higher than even the elevated levels of the early Triassic. The planet was transforming into a world unlike anything that had existed before. A super greenhouse Earth where the normal rules of climate no longer applied. The stage was now set for the most dramatic climate event in Earth's history. The massive quantities of greenhouse gases pumped into the atmosphere by the Rangelia eruptions had created conditions that would make possible something that seems almost impossible: continuous rainfall for 2 million years. The volcanic fury had been unleashed, and its consequences would reshape not just Earth's climate, but the entire course of evolution itself. The great rains were about to begin. In the aftermath of the Rangelia eruptions, Earth's atmosphere had become something alien, something that would be unrecognizable to any creature that breathes oxygen today. The volcanic fury had pumped so much carbon dioxide into the air that the very physics of how our planet trapped and redistributed heat had fundamentally changed. This wasn't just global warming, as we might understand it in modern terms. This was the greenhouse effect, unleashed from all natural constraints, running wild through feedback loops and amplification cycles that turned Earth into a furnace unlike anything in the geological record. To understand what was happening to our planet's atmosphere, we must first grasp the sheer magnitude of the carbon dioxide concentrations that the Rangelia eruptions had created. Modern pre-industrial CO2 levels hover around 280 parts per million, a concentration that had remained relatively stable for thousands of years before human activities began altering it. Today's levels, approaching 420 parts per million, are already driving significant climate change and causing widespread concern among scientists. But during the peak of the post-Rangelia greenhouse, atmospheric CO2 concentrations soared to levels between 1,500 and 2,000 parts per million, nearly 7 times higher than pre-industrial levels and more than quadruple even our current elevated concentrations. These numbers aren't just statistics. They represent a complete transformation of Earth's energy balance. Carbon dioxide molecules have a unique property. They allow visible light from the sun to pass through the atmosphere relatively unimpeded, but they absorb and re-emit infrared radiation, the heat energy that Earth radiates back toward space after absorbing solar energy. Under normal circumstances, this greenhouse effect is what makes Earth habitable, keeping our planet warm enough to support liquid water and complex life. But when CO2 concentrations reach the extreme levels triggered by the Rangelia eruptions, this beneficial warming effect transforms into a runaway process that fundamentally alters how energy moves through the Earth system. The physics of this extreme greenhouse effect created conditions that pushed Earth's climate system into territory it had rarely, if ever, visited before. The massive CO2 concentrations meant that virtually all of the infrared radiation trying to escape to space was being absorbed and re-radiated back toward the surface. Earth was effectively wrapped in a thermal blanket so thick that heat could barely escape, causing surface temperatures to soar to levels that challenged the very boundaries of habitability. Global average temperatures reached 30 to 35 degrees Celsius, temperatures that would make most of the planet's surface uninhabitably hot by modern standards. But the warming wasn't uniform across the globe, and it was the extreme temperature gradients that the greenhouse effect created that would prove crucial to understanding the coming rainfall catastrophe. The massive continental interior of Pangaea, already isolated from oceanic influences by thousands of kilometers of land, became a furnace that regularly reached temperatures exceeding 60 degrees Celsius during summer months. These weren't brief heat waves, but sustained conditions that persisted for months at a time, year after year, decade after decade. The rocks themselves became too hot to touch, and any water that managed to reach these interior regions evaporated almost instantly. Meanwhile, the vast Panthalassa Ocean, while also warmed by the greenhouse effect, retained more moderate temperatures due to water's enormous heat capacity. Ocean surface temperatures in tropical regions reached 35 to 40 degrees Celsius, still brutally hot by modern standards, but significantly cooler than the continental furnace. This temperature differential between land and sea created pressure gradients of unprecedented magnitude, driving atmospheric circulation patterns that would prove capable of moving unimaginable quantities of water vapor from the oceans to the continents. The extreme greenhouse conditions also fundamentally altered the way water vapor behaved in Earth's atmosphere. Warmer air can hold exponentially more water vapor than cooler air, a relationship described by the Clausius-Clapeyron equation that governs atmospheric moisture capacity. Under the scorching conditions created by the post-Rangelia greenhouse effect, the atmosphere could hold nearly 10 times more water vapor than it can today. This wasn't just a theoretical possibility. The superheated oceans were constantly evaporating enormous quantities of water into the atmosphere, creating humidity levels that would be unbearable to any modern organism. The water vapor itself became a crucial component of the runaway greenhouse effect. Water vapor is an even more potent greenhouse gas than carbon dioxide on a molecule-for-molecule basis, and the massive amounts of moisture that the superheated oceans pumped into the atmosphere amplified the warming effect of the volcanic CO2 emissions. This created a positive feedback loop of terrifying power. The more CO2 warmed the planet, the more water evaporated from the oceans, and the more water vapor accumulated in the atmosphere, the more additional warming occurred. This feedback loop was further amplified by changes in cloud behavior under the extreme greenhouse conditions. In normal climate conditions, clouds play a complex role in Earth's energy balance, sometimes cooling the planet by reflecting sunlight back to space, and sometimes warming it by trapping heat near the surface. But under the extreme conditions of the post-Rangelia atmosphere, cloud dynamics became dominated by warming effects. The superheated atmosphere could support massive, towering cloud formations that reached unprecedented heights, trapping enormous amounts of heat near the surface, while also holding unimaginable quantities of water vapor that would eventually fall as rain. The atmospheric chemistry changes triggered by the extreme greenhouse conditions extended far beyond just temperature and humidity. The combination of intense heat, high humidity, and elevated CO2 concentrations created atmospheric conditions that were fundamentally different from anything in Earth's modern climate system. Chemical reactions that normally occur slowly began happening at accelerated rates. The formation of secondary atmospheric compounds proceeded through pathways that don't exist under normal conditions. The very air became a reactive chemical soup that would have been toxic to most forms of life adapted to normal atmospheric conditions. Perhaps most crucially for our story, the extreme greenhouse conditions created atmospheric instability on a scale that the planet had never experienced before. The enormous temperature differentials between the superheated continental interior and the somewhat cooler oceans created convection currents of unprecedented power. These weren't the relatively gentle air movements that drive modern weather patterns, but massive atmospheric circulation systems capable of moving continental-scale air masses with tremendous speed and energy. The jet streams, those high-altitude rivers of fast-moving air that help drive weather patterns, became chaotic and unpredictable under the extreme greenhouse conditions. The normal temperature gradients that maintain stable jet stream patterns were completely disrupted by the uniform warming of the polar regions, causing these atmospheric highways to meander wildly and sometimes break down entirely. This jet stream chaos would prove crucial to understanding how the coming rains could persist for such an unprecedented length of time. The breakdown of normal atmospheric circulation patterns also affected the planet's ability to distribute heat from the equatorial regions toward the poles. Under normal conditions, atmospheric and oceanic circulation systems work together to moderate global temperature differences, preventing any single region from becoming too hot or too cold. But the extreme greenhouse effect disrupted these heat distribution mechanisms, allowing certain regions to become furnaces while others remained merely scorching. The oceanic component of the greenhouse effect was equally dramatic. The superheated oceans didn't just evaporate more water, they also became stratified in ways that prevented normal circulation patterns from functioning. The surface layers became so much warmer than the deeper waters that vertical mixing nearly stopped, creating isolated surface layers that could heat to extraordinary temperatures without losing their energy to the cooler depths. This oceanic stratification meant that the heat absorbed by the oceans stayed trapped near the surface, where it could continue driving evaporation and feeding the atmospheric water vapor feedback loop. The biological effects of these extreme greenhouse conditions were equally profound. Plants, already stressed by the high CO2 concentrations and elevated temperatures, found themselves dealing with atmospheric conditions that challenged the very limits of photosynthesis. The extreme heat and humidity created conditions where many plant species simply couldn't regulate their internal temperature and water balance effectively. Entire ecosystems began showing signs of thermal stress, with widespread plant die-offs further reducing the planet's capacity to absorb excess CO2 and moderate the greenhouse effect. Animal life faced even greater challenges. The combination of extreme heat, toxic atmospheric chemistry, and unprecedented humidity created conditions that pushed the physiological limits of most organisms. Thermoregulation became nearly impossible for large animals in many regions, while smaller creatures found refuge only in underground burrows or other protected microenvironments. The normal ecological relationships that had been rebuilding since the Great Dying were once again disrupted by environmental conditions that exceeded the tolerance limits of most species. As these extreme greenhouse conditions persisted and intensified over hundreds of thousands of years, Earth's climate system approached a critical threshold. The massive atmospheric moisture content, combined with the unprecedented temperature differentials and disrupted circulation patterns, was creating conditions where the normal rules of weather and climate no longer applied. The stage was set for an atmospheric catastrophe that would dwarf even the volcanic eruptions that had triggered it. The beginning of continuous rainfall that would persist for millions of years and reshape the very face of our planet. The moment had arrived when Earth's supercharged atmosphere could no longer contain the impossible burden of water vapor it had been accumulating for hundreds of thousands of years. Like a dam bursting under unimaginable pressure, the sky opened and the great rains began. But this wasn't the gentle onset of a seasonal monsoon, or even the dramatic beginning of a particularly severe storm season. This was the atmospheric equivalent of a geological catastrophe, a meteorological event so extreme and so persistent that it would fundamentally alter the very face of our planet for the next 2 million years. The first drops that fell during what scientists now call the Carnian Pluvial episode carried within them the concentrated fury of an atmosphere pushed beyond all natural limits. These weren't ordinary raindrops formed through the familiar processes of modern weather systems. They were born from atmospheric conditions so extreme that they created precipitation, mechanisms that exist nowhere in Earth's current climate system. The superheated atmosphere, loaded with nearly 10 times the normal moisture content, began releasing its burden through convection processes of unprecedented scale and intensity. To understand what these first moments of the great rains looked like, we must abandon our human-scale understanding of precipitation. Modern thunderstorms, even the most severe ones, pale in comparison to the atmospheric violence that characterized the onset of the Carnian Pluvial episode. The convection columns that formed as the superheated continental interior drew moisture from the surrounding oceans reached heights of 20 kilometers or more, nearly twice as high as the most extreme modern thunderstorms. These weren't isolated storm cells scattered across the landscape, but continent-spanning systems that stretched from horizon to horizon, creating walls of precipitation that moved across Pangaea like slow-motion tsunamis of water falling from the sky. The sheer physics of precipitation under such extreme atmospheric conditions created rainfall intensities that would be incomprehensible to any modern observer. When atmospheric moisture content is 10 times normal levels and temperatures are 15 degrees Celsius above anything in recorded human history, the amount of water that can condense and fall during a single precipitation event increases exponentially. Individual storms during the early phases of the Carnian Pluvial episode likely delivered rainfall totals that exceeded several meters in just a few hours. Precipitation rates that would represent catastrophic flooding under normal circumstances, but which became routine occurrences during this extraordinary period. What made these early rains particularly devastating was not just their intensity, but the way they interacted with landscapes that had been baked and desiccated by hundreds of thousands of years of extreme greenhouse conditions. The continental interior of Pangaea had become a hardpan of sun-baked sediment and rock, completely unprepared to absorb the torrential downpours that were about to become a daily reality. When the first massive precipitation events struck these parched landscapes, the water had nowhere to go but across the surface, creating flash floods of unimaginable magnitude that carved entirely new drainage systems across the supercontinent. The initial flooding events that marked the beginning of the Great Rains were geological processes masquerading as weather phenomena. Rivers that had been reduced to intermittent trickles or had disappeared entirely during the extreme greenhouse phase were suddenly transformed into raging torrents, carrying unprecedented volumes of water and sediment. The Pangaean landscape, which had been stable for millions of years under the arid conditions of the Middle Triassic, began to reshape itself in real time as these new water flows carved valleys, moved mountains of sediment, and created entirely new topographical features. But perhaps most remarkably, the atmospheric conditions that created these initial precipitation events were self-reinforcing in ways that ensured they would continue far longer than any normal weather pattern. The massive evaporation from the newly flooded landscapes pumped even more water vapor into an atmosphere that was already supersaturated with moisture. The latent heat released when this water vapor condensed and fell as rain added enormous amounts of energy to the atmospheric system, powering even more intense convection and creating even more precipitation. Earth had entered a hydrological feedback loop from which there would be no escape for millions of years. The global nature of this precipitation catastrophe became apparent within the first few thousand years of the Carnian Pluvial episode. While the most intense rainfall occurred over the continental landmasses, the extreme atmospheric conditions affected weather patterns across the entire planet. Ocean regions that had never experienced significant precipitation suddenly found themselves beneath persistent cloud cover that blocked out the sun for months at a time. Islands that had existed in stable, arid conditions for millions of years were inundated by rainfall totals that exceeded their entire previous hydrological history. The chemical composition of these early rains tells its own story of atmospheric extremes. The superheated, chemically altered atmosphere of the post-Rangelia world meant that the precipitation falling during the early phases of the Carnian Pluvial episode was far from pure water. High concentrations of dissolved carbon dioxide made the rainwater significantly acidic, with pH levels that would have been harmful to most plant and animal life. Sulfur compounds from the volcanic emissions created acid rain conditions that persisted for hundreds of thousands of years, while trace amounts of heavy metals and other toxic substances contaminated precipitation across the globe. This chemical contamination of the rainfall had profound effects on the landscapes and ecosystems that were being inundated by the great rains. Soils that had been stable for millions of years began to dissolve under the assault of acidic precipitation, releasing their stored nutrients and minerals into the floodwaters that were reshaping the continental surfaces. The chemical weathering rates accelerated by orders of magnitude, creating a planet-wide geochemical experiment as rocks and minerals that had been stable under arid conditions suddenly found themselves exposed to aggressive chemical attack from contaminated rainwater. The biological world's response to the onset of these extraordinary rains was as dramatic as the atmospheric and geological changes they triggered. Plant communities that had adapted to the extreme aridity of the Middle Triassic suddenly found themselves drowning in environments where water was not just abundant, but overwhelming. Many species that had evolved sophisticated drought resistance mechanisms were completely unprepared for the aquatic conditions that the great rains created almost overnight. Entire plant communities that had dominated arid landscapes for millions of years were swept away by the floods or simply rotted in waterlogged soils that their root systems couldn't handle. Yet for some organisms, the beginning of the great rains represented the opportunity of several lifetimes. Species that had survived the arid conditions of the greenhouse phase by retreating to marginal environments near water sources suddenly found the entire continental landscape transformed into habitats they could exploit. Aquatic and semi-aquatic organisms experienced population explosions as temporary lakes, rivers, and wetlands appeared across landscapes that had been bone dry for hundreds of thousands of years. The atmospheric dynamics that sustained these early rains were unlike anything in Earth's meteorological history. The combination of extreme surface heating, unprecedented atmospheric moisture content, and disrupted global circulation patterns created precipitation systems that operated according to different rules than modern weather. Storm systems could persist in the same location for months or even years, continually fed by the enormous moisture reservoirs that the superheated oceans provided. The normal cyclical patterns that govern modern weather, the movement of high and low pressure systems, the seasonal shifts in precipitation patterns, the natural breaks between storm systems, simply didn't exist under the extreme conditions of the early Carnian Pluvial episode. Perhaps most importantly, for understanding how these rains could persist for such an unprecedented length of time, the early phases of the precipitation catastrophe established atmospheric and oceanic circulation patterns that became self-perpetuating. The massive latent heat release from continuous precipitation created permanent low-pressure systems over the continental land masses that continuously drew moist air from the surrounding oceans. The cooling effect of the persistent cloud cover and precipitation created temperature gradients that drove atmospheric circulation patterns completely different from those that had existed during the greenhouse phase. The geological record of these early rains is preserved in sedimentary layers that tell a story of unprecedented environmental change compressed into remarkably short geological timeframes. Rocks that had been accumulating slowly under arid conditions for millions of years were suddenly buried under thick layers of flood deposits, preserving a detailed record of the transition from the extreme greenhouse conditions to the waterlogged world of the Carnian Pluvial episode. These sedimentary layers contain chemical signatures that document not just the intensity of the early precipitation, but also its duration, its chemical composition, and its effects on the landscapes and ecosystems it inundated. As the first millennium of continuous rainfall drew to a close, it became clear that Earth had entered an entirely new climatic state. The great rains had not only begun, they had established the atmospheric and hydrological conditions that would sustain them for an almost incomprehensible length of time. The sky had opened, and it would remain open for the next 2 million years, transforming our planet into something that resembled an alien world more than the Earth we know today. The age of water had begun. As the great rains persisted through their first 100,000 years, Earth began to transform into something that would have been unrecognizable to any observer from the previous eras of our planet's history. This wasn't merely a case of increased precipitation or seasonal flooding. This was the complete submersion of vast continental areas under bodies of water that had no precedent in the geological record. The Carnian Pluvial episode was reshaping the very geography of our planet, creating a waterworld where the familiar boundaries between land and sea became meaningless concepts in a reality dominated by endless expanses of water. The scale of flooding that characterized this aquatic transformation defies easy comprehension. The continental interior of Pangaea, which had been a scorching desert for millions of years, was now covered by a network of interconnected lakes, rivers, and wetlands that stretched from horizon to horizon. These weren't temporary floodplains that would drain when the rain stopped. They were permanent water bodies fed by precipitation so continuous and so voluminous that they established their own hydrological cycles and began to function as inland seas. Some of these newly formed lakes covered areas larger than the modern Mediterranean Sea, while others stretched across distances that would span multiple modern countries. The transformation of Pangaea's topography under the assault of continuous rainfall created entirely new categories of aquatic environments. Regions that had been elevated plateaus became shallow inland seas dotted with islands that were once mountain peaks. Ancient river valleys, carved during earlier wet periods but abandoned during the arid greenhouse phase, were not just refilled but completely overwhelmed, becoming drowned landscapes where the original topography disappeared beneath hundreds of meters of standing water. The familiar concept of drainage basins became obsolete when the entire continental surface was essentially one enormous interconnected water system. Perhaps most remarkably, the continuous rainfall created water bodies in regions where geological structures had never before supported large lakes or rivers. The sheer volume of precipitation was so great that it could maintain permanent water cover even in areas with porous bedrock that would normally allow rapid drainage. Regions with underground cavern systems found themselves transformed into vast underground lakes as surface water poured down through limestone and other soluble rocks, creating subterranean aquatic worlds that connected distant surface water bodies through hidden networks of flooded caves and underground rivers. The chemistry of these vast water bodies was as extraordinary as their scale. The acidic nature of the rainfall, combined with the rapid weathering of rocks and soils under the assault of continuous precipitation, created aquatic environments with chemical compositions unlike anything in modern freshwater or marine systems. These waters carried dissolved minerals and nutrients in concentrations that created entirely new types of aquatic chemistry, supporting microbial communities and chemical processes that had no analogs in Earth's previous or subsequent history. The biological productivity of these newly formed aquatic environments was staggering. The combination of unlimited water, high temperatures, elevated CO2 concentrations, and the massive nutrient inputs from weathering continental rocks created conditions for photosynthetic organisms that were almost impossibly favorable. Algae and other aquatic plants experienced population explosions of unprecedented scale, turning many of the newly formed water bodies into dense, green soups of biological productivity. These massive algal blooms were so extensive that they began to affect the local atmospheric chemistry, producing oxygen in quantities that created localized atmospheric conditions unlike anything in the surrounding terrestrial environments. The interconnected nature of these water systems meant that the biological productivity occurring in one region could affect aquatic environments hundreds or even thousands of kilometers away. Nutrients, produced by algal blooms in highland lakes, were carried by the continuous water flows to lowland areas, where they triggered secondary blooms that supported entirely different communities of organisms. The result was a continental-scale aquatic ecosystem, where biological productivity in one location could cascade through the water network to affect life across vast distances. The marine environment underwent equally dramatic transformations as sea levels rose in response to the massive volumes of water being added to the global hydrological system. The continuous rainfall wasn't just filling continental depressions, it was also raising the overall volume of water in the world's oceans to levels that hadn't been seen since the earliest phases of Earth's history. Coastal regions that had been stable for millions of years found themselves hundreds of kilometers underwater as the rising seas advanced across the continental margins at rates that would have been catastrophic under normal circumstances. This sea level rise wasn't uniform across the globe, and the complex interactions between the rising waters and the existing continental topography created new marine environments that had no precedent in Earth's history. Shallow continental seas extended far into what had previously been terrestrial environments, creating vast areas of brackish water where fresh water from the continuous rainfall mixed with seawater from the rising oceans. These transitional environments supported unique biological communities that combined freshwater and marine organisms in ecological relationships that had never before existed on Earth. The tidal dynamics in these newly expanded marine environments were completely different from anything in the modern ocean system. The vast extent of shallow water areas created tidal bores and other extreme tidal phenomena that moved enormous volumes of water across continental distances twice each day. These tidal movements weren't just physical processes, they became major mechanisms for distributing nutrients, organisms, and chemical compounds across the interconnected aquatic systems that now covered much of Earth's surface. The atmospheric effects of having such vast areas of the planet covered by standing water were as dramatic as the direct physical changes to the landscape. The enormous surface area of all these water bodies created evaporation rates that sustained the atmospheric moisture levels necessary to continue the great rains, but they also created local weather patterns that were completely unlike anything in Earth's previous climate history. Massive thunderstorm systems formed over the warm water surfaces and then moved inland, where they encountered other storm systems forming over different water bodies, creating atmospheric interactions of unprecedented complexity and intensity. The thermal effects of these vast water bodies also began to moderate some of the extreme temperature fluctuations that had characterized the greenhouse phase before the rains began. Water has an enormous heat capacity compared to land surfaces, and the presence of so much standing water began to create more stable temperature conditions in many regions. However, this temperature moderation wasn't uniform, and the complex interactions between different water bodies, local topography, and atmospheric circulation created microclimates that ranged from relatively temperate to still brutally hot, sometimes within distances of just a few kilometers. The sedimentary processes occurring in these vast aquatic systems were reshaping Earth's geological record in real time. The continuous rainfall was eroding enormous quantities of sediment from highland areas and depositing it in the lowland water bodies. But the scale of these processes was far beyond anything in normal geological experience. Some of the newly formed lakes were accumulating sediment at rates measured in meters per century rather than the millimeters per century typical of normal lacustrine environments. These rapid sediment accumulation rates were preserving detailed records of environmental conditions and biological activity at temporal resolutions that provide modern scientists with an almost year-by-year account of how the flooded world evolved during the Carnian Pluvial episode. The geochemical cycles operating in this waterlogged world were equally extraordinary. The massive surface area of standing water created conditions where atmospheric gases could dissolve into aquatic systems at rates that significantly affected global atmospheric composition. The vast algal blooms were consuming CO2 and producing oxygen at scales that began to moderate some of the extreme atmospheric conditions that had triggered the great rains in the first place. However, the decomposition of organic matter in the oxygen-depleted depths of many water bodies was also producing methane and other greenhouse gases that complicated these atmospheric interactions. Perhaps most remarkably, the sheer persistence of these flooded conditions began to create positive feedback loops that ensured their own continuation. The vast water surfaces maintained high atmospheric humidity levels that sustained the rainfall patterns, while the biological productivity in the aquatic systems created atmospheric chemistry, changes that supported continued precipitation. The thermal mass of so much standing water stabilized regional climate systems in ways that made the extreme weather patterns of the early Carnian Pluvial episode self-perpetuating. As hundreds of thousands of years passed with these conditions persisting and intensifying, it became clear that Earth had entered a fundamentally different state of hydrological organization. This wasn't a temporary climate anomaly that would eventually return to previous conditions. This was a new way of organizing water, atmosphere, and life that would persist for millions of years and reshape the evolutionary trajectory of life on our planet. The world had become truly underwater, not just physically, but in terms of the basic organizing principles that governed how Earth's surface systems functioned. In a world where the sun had become a stranger and water fell from the sky, with the persistence of gravity itself, life faced the ultimate test of adaptability. For creatures that had evolved over millions of years in the scorching deserts of Pangaea, the transformation to a waterlogged planet represented an evolutionary challenge unlike anything in Earth's history. Yet rather than simply perishing en masse, life responded to the endless deluge with a creativity and resilience that would reshape the very foundations of biological diversity for the remainder of Earth's history. The most immediate challenge facing terrestrial organisms was the simple problem of finding dry land. In a world where vast areas of previously stable continental surface had been submerged beneath permanent lakes and wetlands, the very concept of terrestrial habitat had to be redefined. High ground became the most precious real estate on the planet, with elevated areas that remained above the floodwaters, supporting refugee populations of organisms that had been displaced from their traditional habitats. These biological refugees were forced into unnaturally high population densities on the remaining dry land, creating competition pressures that drove rapid evolutionary change as species adapted to crowded conditions and limited resources. But the most remarkable aspect of life's response to the great rains was not how organisms retreated from the water, but how they embraced it. The endless precipitation created vast new aquatic and semi-aquatic habitats that had never existed before in Earth's history, and these environments became evolutionary laboratories where entirely new forms of life could experiment with adaptations that had previously been impossible or unnecessary. Organisms that had spent millions of years adapting to arid conditions suddenly found themselves with opportunities to explore aquatic lifestyles that their ancestors could never have imagined. Plant life underwent perhaps the most dramatic transformations during the endless storm. Species that had evolved sophisticated water conservation mechanisms, thick waxy leaves, deep root systems, and specialized tissues for storing scarce moisture, suddenly found these adaptations not just unnecessary, but actually counterproductive in environments where water was overwhelmingly abundant. Natural selection began favoring plants that could thrive in waterlogged soils, leading to the rapid evolution of species with specialized root systems that could function in oxygen-depleted, permanently saturated substrates. The most successful plants during this period were those that could take advantage of the unique conditions created by the continuous rainfall. Ferns, which had been relatively minor components of Triassic plant communities, experienced an evolutionary explosion as they colonized the vast new wetland habitats that the great rains had created. These weren't the delicate ferns of modern forest understories, but massive tree-sized species that could dominate entire landscapes. Some species evolved hollow stems and specialized air transport systems that allowed them to grow in standing water, while others developed floating capabilities that let them colonize the surfaces of the newly formed lakes and rivers. The conifer forests that had dominated many terrestrial environments during the arid phase faced their own unique challenges and opportunities. Many species developed remarkable adaptations to the continuously wet conditions, including modified root systems that could function as both anchors and breathing apparatus in waterlogged soils. Some conifers evolved the ability to reproduce and complete their entire life cycles while partially submerged, with specialized cone structures that could release seeds into aquatic environments where they would germinate and establish new populations. Perhaps most remarkably, entirely new categories of plants evolved to fill the ecological niches created by the unique environmental conditions of the endless storm. Aquatic flowering plants, though still millions of years away from their evolutionary debut, were preceded by primitive aquatic gymnosperms that developed many of the same adaptations that would later characterize true aquatic flowering plants. These evolutionary experiments in aquatic plant life created biological communities that had no analogs in either earlier or later periods of Earth's history. Animal life faced equally dramatic challenges and opportunities in the waterlogged world of the Carnian Pluvial episode. Large terrestrial animals that had dominated the arid landscapes of the Middle Triassic found themselves in an environment where their size and specializations for dry conditions became significant disadvantages. Many of the massive archosaurs that had ruled the pre-rain ecosystems simply couldn't adapt quickly enough to the rapidly changing conditions, leading to local extinctions that opened up ecological niches for smaller, more adaptable organisms. The early dinosaurs that had been minor players in the pre-rain world suddenly found themselves with unprecedented opportunities. Their small size, which had been a disadvantage when competing with giant archosaurs for resources in arid environments, became a crucial advantage in the flooded world, where agility and adaptability were more important than sheer size. Some dinosaur lineages began developing semi-aquatic adaptations, with modifications to their limbs and respiratory systems that allowed them to exploit the abundant aquatic resources that the great rains had created. The amphibian renaissance that occurred during the endless storm was perhaps the most dramatic example of how the changed conditions favored organisms pre-adapted to aquatic life. Amphibians, which had been declining in diversity and abundance during the arid conditions of the Middle Triassic, suddenly found themselves in a world perfectly suited to their dual terrestrial aquatic lifestyle. Populations exploded as vast new breeding habitats appeared across landscapes that had been completely unsuitable for amphibian reproduction just centuries earlier. But the most remarkable amphibian adaptations during this period were not just expansions of traditional amphibian lifestyles, but evolutionary experiments in completely aquatic existence. Some lineages developed enlarged gills and other modifications that allowed them to remain aquatic throughout their entire life cycles, while others evolved specialized adaptations for life in the deep waters of the newly formed lakes. These aquatic amphibians became the dominant vertebrate predators in many freshwater environments, occupying ecological roles that would later be filled by fish and other fully aquatic vertebrates. The insect world experienced its own revolution in response to the endless rains. The vast new wetland habitats created unprecedented opportunities for insects with aquatic larval stages, leading to evolutionary radiations of flies, beetles, and other groups that could exploit both terrestrial adult habitats and aquatic breeding environments. Some insect lineages evolved complete aquatic lifestyles for the first time in their evolutionary history, developing gills, swimming appendages, and other modifications that allowed them to colonize the deep water environments that had never before existed in their terrestrial ancestral habitats. Perhaps most importantly, the insect communities that evolved during the endless storm established many of the ecological relationships that would later become fundamental to terrestrial ecosystems. The coevolution of plants and insects in the unique environments created by the great rains led to innovations in pollination, herbivory, and decomposition that would persist long after the rains ended and would form the foundation for many of the ecological processes that characterize modern terrestrial ecosystems. The microbial world underwent equally dramatic changes during the endless storm, though these changes were largely invisible to any potential observers of the time. The vast new aquatic environments created opportunities for microbial communities that had never before existed on such scales in Earth's history. Bacterial and archaeal communities that had been restricted to small, specialized habitats during the arid phase suddenly found themselves with continent-sized environments to colonize and exploit. The biogeochemical cycles that these microbial communities established in the flooded world were unlike anything in Earth's previous history. The combination of unlimited water, high temperatures, elevated atmospheric CO2, and massive inputs of nutrients from weathering rocks created conditions where microbial metabolism could proceed at rates and scales that significantly affected global atmospheric and oceanic chemistry. Some microbial communities became so productive that they created localized atmospheric conditions that were detectably different from the surrounding environments. Perhaps most remarkably, the endless storm created conditions where different forms of life could interact in ways that had never been possible before. The interconnected nature of the vast aquatic systems meant that organisms and their metabolic products could move across continental distances, creating biological and chemical connections between ecosystems that were thousands of kilometers apart. These long-distance biological interactions established ecological relationships that would persist long after the great rains ended and would influence the evolution of life for millions of years to come. As the endless storm persisted through its first million years, it became clear that life had not simply survived the transformation to a waterlogged world. It had embraced the new conditions and was using them as an opportunity for evolutionary innovation on an unprecedented scale. The Great Rains had created not just new environments, but entirely new possibilities for what life could become. In the endless storm, evolution itself had found new ways to create diversity, establish relationships, and explore the boundaries of biological possibility. As the Great Rains thundered into their second million years, the very success of life's adaptation to the waterlogged world began to sow the seeds of its own destruction. The endless deluge that had created unprecedented opportunities for evolutionary innovation was simultaneously creating environmental conditions so extreme that they pushed many organisms beyond their physiological limits. What had begun as an explosion of biological diversity and productivity was about to transform into one of the most severe extinction events in Earth's history, a second great dying that would rival the Permian catastrophe in its scope and devastation. The irony of this impending catastrophe lay in its origins within the very processes that had initially made the Carnian Pluvial episode such a boon for biological diversity. The massive productivity of algae and other photosynthetic organisms in the newly formed aquatic environments had initially seemed like an unqualified success story. Creating food webs of unprecedented complexity and supporting biological communities larger and more diverse than anything Earth had seen since before the Permian extinction. However, this biological success contained within it the mechanisms of its own undoing, as the very processes that sustained life in the waterlogged world began to create chemical and physical conditions that would prove lethal to the organisms that had evolved to exploit them. The first signs of impending ecological collapse appeared in the deep waters of the vast lake systems that covered much of Pangaea's interior. The enormous quantities of organic matter produced by surface-dwelling algae and plants began to sink into the deeper layers of these water bodies, where they encountered environmental conditions that were fundamentally different from the well-oxygenated surface waters where they had been produced. In these depths, bacterial decomposition processes consumed the available oxygen at rates that far exceeded the ability of atmospheric exchange and photosynthetic oxygen production to replenish it. The result was the development of vast anoxic zones in the deeper waters of many aquatic systems, regions where oxygen concentrations dropped to levels that could not support most forms of complex life. These anoxic conditions didn't develop gradually over geological timescales, but spread rapidly through interconnected water systems as the continuous input of organic matter overwhelmed the limited oxygen processing capacity of the deep water environments. Within relatively short periods, measured in thousands rather than millions of years, entire aquatic ecosystems found their deeper layers transformed into lifeless chemical environments dominated by anaerobic bacterial processes. The chemical consequences of widespread anoxia were far more severe than simple oxygen depletion. In the absence of oxygen, bacterial decomposition processes shifted to alternative pathways that produced hydrogen sulfide, methane, and other toxic compounds that began to accumulate in the deeper waters of the flooded continental systems. Hydrogen sulfide, in particular, became a major killer as it reached concentrations that were lethal not only to aquatic organisms, but also to terrestrial life when these toxic waters occasionally mixed with surface layers or when gases escaped from the water into the overlying atmosphere. The toxification of deep waters created a cascading series of ecological collapses that spread throughout the interconnected aquatic systems of the flooded world. Fish and other aquatic vertebrates that had evolved to exploit the deep water environments found themselves facing not just oxygen depletion, but active poisoning by the toxic compounds produced by anaerobic decomposition. Many species that had successfully adapted to aquatic life during the early phases of the Great Rains were eliminated entirely as their habitats became chemically hostile to complex life. The marine environments were experiencing their own version of this chemical catastrophe, but on an even larger scale. The continuous input of fresh water from the Great Rains had created massive areas of stratified ocean water, where less dense freshwater layers floated on top of denser, saltier deep water. This stratification prevented the normal mixing processes that distribute oxygen throughout the ocean column, leading to the development of anoxic conditions in vast areas of the world's oceans. The scale of marine anoxia during this period was so extensive that it created what paleontologists call black shale events, periods when oxygen-depleted ocean waters became so widespread that they left distinctive chemical signatures in sedimentary rocks around the world. The atmospheric consequences of these widespread anoxic conditions began to create global environmental changes that affected even organisms living in well-oxygenated surface environments. The massive production of hydrogen sulfide from anoxic waters began to affect local and regional atmospheric chemistry, creating air quality conditions that were toxic to many terrestrial organisms. In some regions, the atmosphere itself became periodically unbreathable as hydrogen sulfide concentrations reached levels that could kill even organisms that were not directly dependent on aquatic environments. Perhaps most devastatingly, the chemical changes occurring in the flooded world began to disrupt the very atmospheric processes that had sustained the Great Rains for so long. The massive algal die-offs that occurred when aquatic environments became too toxic to support photosynthetic life, reduced the biological processes that had been moderating atmospheric CO2 concentrations. As these biological carbon sinks disappeared, atmospheric greenhouse gas concentrations began to rise again, threatening to return Earth to the extreme greenhouse conditions that had preceded the Great Rains. The biological communities that had seemed so successful during the early phases of the Carnian Pluvial episode found themselves facing environmental conditions that changed faster than evolutionary processes could respond. Species that had evolved specialized adaptations to the stable aquatic conditions of the early flood period discovered that their highly specialized traits made them vulnerable to the rapidly changing chemical conditions of the later phases. The very specificity of their adaptations, which had made them so successful in exploiting the unique environments of the waterlogged world, became a liability when those environments began to deteriorate. The extinction patterns that emerged during this phase of the Carnian Pluvial episode were particularly cruel in their selectivity. Many of the most successful and innovative organisms of the early flood period, the species that had most completely adapted to aquatic life, that had evolved the most sophisticated mechanisms for exploiting waterlogged environments, that had achieved the highest levels of specialization for the unique conditions of the endless storm, were precisely the species that were least capable of surviving when those conditions began to change. The generalists and opportunists that had seemed less successful during the boom times of the early flood period often proved more capable of surviving the chemical and physical challenges of the deteriorating aquatic environments. The terrestrial ecosystems that had retreated to high ground during the flooding phase faced their own unique extinction pressures as the chemical deterioration of aquatic environments began to affect atmospheric conditions across the entire planet. Many plant communities that had successfully adapted to life on the remaining dry land found themselves dealing with air quality issues and soil chemistry changes that resulted from the toxic compounds being released from nearby aquatic systems. The interconnected nature of the flooded world meant that local environmental problems could quickly become regional or even continental scale disasters. The cascading nature of these ecological collapses created positive feedback loops that accelerated the rate of environmental deterioration. As more organisms died and contributed to the organic loading of aquatic systems, anoxic conditions spread more rapidly and became more severe. As more aquatic environments became toxic, the biological processes that had been moderating atmospheric chemistry became less effective, leading to further atmospheric deterioration that stressed terrestrial ecosystems. The very interconnectedness that had made the flooded world so successful during its early phases became a liability that allowed local problems to propagate throughout the entire system. The geological record of this extinction event preserves evidence of environmental conditions so severe that they challenge our understanding of the limits of habitability. Sedimentary layers from this period contain chemical signatures indicating hydrogen sulfide concentrations in some aquatic environments that would have been lethal to virtually all forms of complex life. Carbon isotope ratios indicate massive disruptions to global carbon cycling as biological processes collapsed on continental scales. The fossil record shows diversity crashes that rival those of the end Permian extinction in their severity and rapidity. Yet even as this second great dying devastated the biological communities that had flourished during the early phases of the endless storm, it was also creating the conditions for the next great evolutionary innovation in Earth's history. The mass extinction was eliminating the specialized organisms that had dominated the waterlogged world, but it was also creating ecological opportunities for the survivors, organisms that possessed the flexibility and resilience necessary to survive rapidly changing environmental conditions. Among these survivors were the early dinosaur lineages that had remained relatively generalized and adaptable throughout the environmental upheavals of the Carnian Pluvial episode. As the Great Dying progressed through its most severe phases, it became clear that this wasn't just another extinction event, but a fundamental reset of Earth's biological systems that would reshape the trajectory of evolution for the remainder of the Mesozoic era. The endless storm had created and then destroyed entire categories of life, but in doing so, it had cleared the ecological stage for the rise of the organisms that would define the next chapter in Earth's biological history. In the wake of the Second Great Dying, as toxic waters receded and poisoned atmospheres slowly cleared, Earth presented a biological landscape that was simultaneously devastated and pregnant with unprecedented evolutionary potential. The mass extinction had swept away the dominant life forms that had ruled both the arid pre-rain world and the aquatic environments of the early Carnian Pluvial episode, leaving behind ecological vacuums on a scale that hadn't existed since the aftermath of the Permian catastrophe. But this time, the survivors were different. They were organisms that had been tempered by 2 million years of the most extreme environmental conditions in Earth's history. Creatures that possessed an evolutionary resilience and adaptability that would soon remake the entire biological world. Among these survivors, one group stood poised to seize the moment with an evolutionary audacity that would define the next 165 million years of Earth's history. The dinosaurs, those small and seemingly insignificant archosaurs that had skulked in the shadows throughout the Triassic period, emerged from the chaos of the Great Dying as the inheritors of a planet whose rules had been completely rewritten. What had once been evolutionary disadvantages, their relatively small size, their high metabolic rates, their lack of specialized adaptations to either extreme aridity or permanent aquatic conditions, suddenly became the keys to success in a world where flexibility and rapid adaptation were the primary currencies of survival. The ecological opportunities that presented themselves to these early dinosaur survivors were unlike anything that had existed in Earth's previous history. The extinction of the giant archosaurs that had dominated terrestrial ecosystems for millions of years left vacant the role of large terrestrial predator, while the collapse of specialized herbivorous lineages created openings for organisms that could exploit plant resources in new and innovative ways. But perhaps most importantly, the environmental conditions that persisted in the aftermath of the Great Dying, the residual effects of 2 million years of continuous rainfall, the altered atmospheric chemistry, the transformed landscapes, created selective pressures that favored exactly the kinds of evolutionary innovations that would make dinosaurs the most successful vertebrate group in Earth's history. The first and most crucial advantage that dinosaurs possessed in this post-extinction world was their advanced respiratory system, an evolutionary innovation that had initially evolved as an adaptation to the low oxygen conditions that periodically affected Triassic environments. This system, which involved a complex network of air sacs connected to the lungs, allowed dinosaurs to extract oxygen from the air with far greater efficiency than other vertebrate groups. In the aftermath of the Great Dying, when atmospheric oxygen levels had been depleted by massive decomposition processes and when many environments still contained toxic gases, This respiratory advantage became a decisive factor in determining which organisms could successfully colonize the recovering ecosystems. The metabolic advantages that dinosaurs had evolved during their millions of years as small, active predators also proved crucial in the post-extinction environment. Unlike the large, cold-blooded archosaurs that had dominated pre-rain ecosystems, dinosaurs possessed metabolic systems that were intermediate between cold-blooded and warm-blooded conditions, what scientists now call mesothermic. This gave them the ability to maintain higher activity levels than purely cold-blooded creatures while requiring less food than fully warm-blooded animals would need. In a world where food webs were still recovering from mass extinction and where resources were often unpredictable, this metabolic flexibility provided a crucial survival advantage. But perhaps the most important factor in dinosaur success was their evolutionary flexibility, their ability to rapidly adapt to new ecological roles and environmental conditions. Unlike the highly specialized creatures that had dominated earlier ecosystems, dinosaurs retained a basic body plan that was remarkably adaptable to different lifestyles and environmental niches. Their hip structure, limb proportions, and skull architecture could be modified relatively easily through evolutionary processes to create forms adapted to everything from small insectivory to massive herbivory to aquatic life. The diversification of dinosaur lineages during the recovery from the Carnian extinction was extraordinarily rapid by normal evolutionary standards. Within just a few million years, dinosaur groups had evolved to fill ecological roles that had been vacant since the mass extinction, but they didn't simply replace the extinct forms with similar creatures. Instead, they evolved entirely new approaches to being large terrestrial animals, creating biological solutions to ecological problems that had never been tried before in Earth's history. The evolution of large herbivorous dinosaurs represented one of the most remarkable biological innovations of this period. The plant communities that had survived the Great Dying were different from those that had existed before the extinction. They included new growth forms, new chemical compositions, and new ecological relationships that had evolved during the unique conditions of the endless storm. The dinosaurs that evolved to exploit these plant resources didn't simply become larger versions of the herbivorous archosaurs that had been eliminated by the extinction. Instead, they developed entirely new approaches to plant processing, including sophisticated dental batteries, complex digestive systems, and feeding strategies that allowed them to extract energy from plant materials that had been unexploitable by previous herbivorous lineages. The predatory dinosaurs that evolved during this period were equally innovative in their approaches to carnivory. Rather than simply scaling up the predatory strategies that had been successful for smaller Triassic dinosaurs, they evolved new hunting techniques, new biomechanical solutions for killing large prey, and new social behaviors that allowed them to exploit the abundant herbivorous resources that their plant-eating relatives were providing. Some lineages experimented with pack hunting strategies that had never been seen in terrestrial vertebrates, while others evolved to massive sizes that allowed them to hunt prey much larger than themselves. But the most remarkable aspect of dinosaur evolution during this period was not just their diversification into different ecological roles, but their innovation in creating entirely new categories of vertebrate lifestyle. Some dinosaur lineages evolved powered flight independently of any other vertebrate group, creating the pterosaurs that would dominate aerial environments for over 100 million years. Others evolved semi-aquatic lifestyles that combine terrestrial mobility with aquatic feeding strategies, exploiting the abundant aquatic resources that persisted from the flood period. Still, others evolved gigantism to scales that had never been achieved by terrestrial vertebrates, creating ecosystems dominated by animals whose size and ecological impact had no precedent in Earth's history. The plant communities that recovered from the Great Dying were themselves undergoing rapid evolutionary change, and the co-evolution between dinosaurs and plants during this period established many of the ecological relationships that would characterize terrestrial ecosystems for the remainder of the Mesozoic era. The browsing pressure from increasingly diverse herbivorous dinosaurs drove the evolution of new plant defense mechanisms, new growth strategies, and new reproductive approaches. Some plant lineages evolved to enormous sizes to escape herbivorous pressure, creating the first forests dominated by truly gigantic trees. Others evolved chemical defenses, physical barriers, or rapid growth strategies that allowed them to persist despite intense herbivory. The atmospheric and climatic conditions that persisted in the aftermath of the Great Dying continued to favor the evolutionary success of dinosaur lineages. The elevated CO2 levels and warm temperatures that remained from the volcanic episodes and greenhouse effects of the Carnian Pluvial episode created conditions where large, active animals could thrive without the energy constraints that would limit their success under cooler, low CO2 conditions. The absence of polar ice and the resulting warm temperatures at high latitudes meant that dinosaurs could colonize the entire globe, establishing populations from equatorial regions to what would become the Arctic and Antarctic. The geographic distribution of recovering ecosystems also played a crucial role in dinosaur success. The environmental changes caused by the Great Rains had created a more geographically homogeneous world than had existed before the Carnian Pluvial episode. Similar environmental conditions extended across much larger geographic areas, allowing successful dinosaur lineages to spread rapidly across vast continental distances and establish populations that were large enough to support continued evolutionary innovation. Perhaps most importantly, the timing of dinosaur diversification coincided with a period of relatively stable environmental conditions that allowed evolutionary experiments to persist long enough to become established lineages. Unlike the rapidly changing conditions that had characterized the height of the Carnian Pluvial episode, the post-extinction environment provided a window of stability that lasted several million years, long enough for new evolutionary innovations to be tested, refined, and established as permanent features of dinosaur biology. The success of dinosaurs during this period wasn't just a matter of filling vacant ecological roles left by extinct competitors. They were actively creating new ecological possibilities, establishing new types of ecosystem relationships, and exploring biological solutions that had never been attempted before. Their evolutionary success fundamentally altered the rules governing terrestrial ecosystems, creating biological communities that operated according to principles that had no precedent in Earth's previous history. As the recovery from the Great Dying progressed, it became clear that dinosaurs weren't just the beneficiaries of evolutionary opportunity. They were actively reshaping the biological world in ways that would persist for over 100 million years and continue to influence terrestrial ecosystems even after their eventual extinction. The endless storm had created the conditions for evolution's greatest opportunity, and dinosaurs had seized that opportunity with an evolutionary creativity and success that would make them the definitive rulers of the Mesozoic world. After 2 million years of continuous precipitation, after countless generations of organisms had lived and died, knowing only a world where water fell endlessly from gray skies, something extraordinary began to happen. The great rains started to weaken. This wasn't a sudden cessation, like turning off a cosmic faucet, but rather a gradual diminishment that played out over hundreds of thousands of years as Earth's climate system slowly found its way back to a new equilibrium. The atmospheric conditions that had sustained the Carnian Pluvial episode for such an unprecedented length of time were finally beginning to exhaust themselves, and the planet was about to undergo yet another fundamental transformation that would reshape both its physical landscape and its biological communities. The mechanisms that brought about the end of the Great Rains were as complex and interconnected as those that had sustained them for so long. The massive carbon dioxide concentrations that had driven the extreme greenhouse conditions were finally beginning to be drawn down by the very biological and geological processes that the endless storm had set in motion. The enormous productivity of plant life during the wet period had locked away vast quantities of atmospheric carbon in the form of organic matter that accumulated in swamps, lakes, and marine sediments. These carbon deposits, buried under layers of sediment and removed from contact with the atmosphere, represented a planetary-scale carbon sequestration process that gradually reduced the greenhouse gas concentrations that had maintained the extreme weather patterns. Equally important was the role of enhanced rock weathering in removing carbon dioxide from the atmosphere. The continuous rainfall and warm temperatures of the Carnian Pluvial episode had accelerated chemical weathering processes to rates far beyond anything in Earth's normal climate system. As rainfall dissolved minerals from exposed rocks, the resulting chemical reactions consumed atmospheric CO2 and locked it away in the form of carbonate minerals that accumulated in ocean sediments. After 2 million years of this enhanced weathering, the cumulative effect was a significant reduction in atmospheric greenhouse gas concentrations that undermined the chemical foundations of the extreme climate system. The changing atmospheric composition had cascading effects throughout Earth's climate system that accelerated the transition away from the conditions that had sustained the Great Rains. As CO2 concentrations decreased, global temperatures began to moderate, reducing the atmosphere's capacity to hold the enormous quantities of water vapor that had fueled the continuous precipitation. The thermal gradients between continental interiors and ocean surfaces, which had driven the massive convection systems responsible for the endless storms, began to weaken as the extreme temperature differences moderated. The biological feedback loops that had helped sustain the Carnian Pluvial episode also began to shift in ways that reduced rather than amplified the conditions for continuous rainfall. The massive algal blooms and other photosynthetic activity in the flooded environments had initially released enormous quantities of water vapor through transpiration and evaporation, contributing to atmospheric moisture levels. But as these aquatic ecosystems matured and began to develop more balanced community structures, their net contribution to atmospheric moisture decreased. The establishment of more diverse and stable aquatic food webs meant that more of the biological productivity was being recycled within the ecosystems rather than contributing to atmospheric processes. The geographical changes that had resulted from 2 million years of continuous erosion and sedimentation also played a role in altering the climate dynamics that had sustained the Great Rains. The massive redistribution of sediment from highland areas to lowland basins had created new topographical patterns that affected atmospheric circulation in subtle but important ways. Mountain ranges had been worn down by continuous erosion, reducing their ability to force air masses upward and trigger precipitation. Meanwhile, the accumulation of sediment in lowland areas had filled in many of the depressions that had served as moisture sources and convection centers during the height of the flood period. Perhaps most importantly, the volcanic activity that had triggered the Carnian Pluvial episode was finally beginning to wane. The Rangelia Large Igneous Province, which had been pumping greenhouse gases into the atmosphere for millions of years, was entering a period of reduced activity as the mantle plume that had driven the eruptions began to weaken. Without the continuous input of volcanic CO2 and other greenhouse gases, the atmospheric chemistry that had sustained the extreme climate conditions began to shift toward more moderate compositions. The transition away from the conditions of the endless storm wasn't uniform across the globe, and different regions experienced the return to more normal precipitation patterns at different times and in different ways. The continental interiors, which had been the most dramatically affected by the extreme weather of the Carnian Pluvial episode, were among the first to show signs of moderating conditions. The massive low-pressure systems that had dominated these regions for millions of years began to weaken and break up, allowing high-pressure systems and more variable weather patterns to reestablish themselves. Coastal regions, which had been somewhat buffered from the most extreme conditions by their proximity to the oceans, experienced a more gradual transition. The marine environments that had been altered by the great rains, the areas of reduced salinity, altered circulation patterns, and modified chemical composition, took longer to return to more typical oceanic conditions. The thermal inertia of the vast water masses meant that oceanic temperatures remained elevated for hundreds of thousands of years after atmospheric conditions began to moderate. The biological communities that had evolved during the endless storm faced their own complex challenges as environmental conditions began to shift once again. Many of the species that had become highly specialized for life in permanently waterlogged environments found themselves dealing with gradually drying conditions that favored different types of adaptations. Some aquatic and semi-aquatic lineages were able to track their preferred habitats as they retreated to lower elevations and more permanently wet areas, while others were forced to evolve new adaptations or face extinction. The plant communities showed particularly dramatic responses to the changing conditions. The massive fern forests and other wetland-adapted vegetation that had dominated the landscape during the height of the flood period began to give way to more drought-tolerant species as soil conditions shifted from permanently saturated to merely well-watered. This wasn't a return to the extreme arid conditions that had characterized the pre-rain period, but rather the establishment of more moderate, seasonally variable precipitation patterns that represented a new climate equilibrium. The transition period also saw the emergence of entirely new types of plant communities that combined adaptations evolved during the wet period with features that allowed them to survive under more variable moisture conditions. These hybrid plant communities represented evolutionary experiments in dealing with climatic uncertainty, and many of the adaptations that evolved during this transition period would prove crucial for plant success during the remainder of the Mesozoic era. Animal communities experienced equally complex changes as the great rains diminished. The aquatic ecosystems that had supported enormous populations of fish, amphibians, and other water-dependent organisms began to contract as water levels receded and many temporary water bodies dried up entirely. This contraction of aquatic habitats created intense competition for the remaining water resources and drove rapid evolutionary change in many lineages as they adapted to life in more restricted and variable aquatic environments. The terrestrial ecosystems that had been relegated to highland refugia during the height of the flooding began to expand back into areas that had been underwater for millions of years. But these weren't simply expansions of pre-existing communities into familiar territories. The landscapes that emerged as the waters receded were fundamentally different from those that had been submerged, with new soil compositions, altered topographies, and novel combinations of environmental conditions. The dinosaur communities that had evolved and diversified during the chaotic conditions of the Carnian Pluvial episode found themselves inheriting a world that was more stable and predictable than anything their lineages had experienced for millions of years. The moderating climate conditions allowed for the establishment of more consistent food webs and more stable territorial relationships, providing the environmental foundation for the evolution of the massive, long-lived dinosaur species that would characterize the remainder of the Mesozoic era. As the last of the great rains finally ceased and Earth's weather patterns settled into the more moderate but still warm conditions that would characterize the late Triassic, it became clear that the planet had undergone a transformation as fundamental as any in its history. The endless storm had not just been a period of extreme weather. It had been a complete reorganization of Earth's surface systems, atmospheric chemistry, and biological communities. The world that emerged from the 2 million years of rain was fundamentally different from the world that had entered it, and the changes that had occurred during this extraordinary period would influence the trajectory of life on Earth for the next 150 million years. As we stand at the end of this extraordinary journey through 2 million years of continuous rainfall, we find ourselves confronting a story that transcends the boundaries of ancient history to speak directly to our modern world. The Carnian Pluvial episode wasn't just a fascinating geological curiosity buried in the deep past. It was a masterclass in how Earth's climate system responds to extreme disruption, a textbook example of how life adapts to seemingly impossible conditions, and perhaps most importantly, a mirror that reflects our own relationship with a planet whose climate we are rapidly altering through our own industrial activities. The parallels between the ancient world of the Great Rains and our contemporary climate crisis are both striking and sobering. Just as the massive volcanic emissions of the Rangelia Large, igneous province pumped unprecedented quantities of greenhouse gases into the Triassic atmosphere, our modern industrial civilization is conducting its own massive experiment in atmospheric chemistry by burning fossil fuels at rates that are injecting carbon dioxide into the atmosphere faster than at any time in human history. The atmospheric CO2 concentrations that we are creating today are approaching levels that haven't been seen since the most extreme phases of the Mesozoic greenhouse worlds. And the rate at which we are adding these gases to the atmosphere may be even faster than the volcanic processes that triggered the Carnian Pluvial episode. But the lessons of the Great Rains extend far beyond simple comparisons of greenhouse gas concentrations. The Carnian Pluvial episode demonstrates with startling clarity how complex systems can reach tipping points where relatively small changes trigger cascading transformations that reshape entire planets. The volcanic emissions that started the Great Rains were certainly massive by human standards, but they represented only a small fraction of Earth's total carbon budget. What made them so transformative was not their absolute magnitude, but the way they interacted with existing atmospheric, oceanic, and biological systems to create feedback loops that amplified their effects far beyond what their initial impact might have suggested. The feedback mechanisms that sustained the Great Rains for 2 million years provide particularly relevant insights for understanding how our own climate system might respond to continued greenhouse gas emissions. The water vapor feedback that helped maintain the extreme precipitation patterns of the Carnian Pluvial episode operates in our modern climate system as well, and climate scientists recognize it as one of the most important factors that will determine how much warming results from our fossil fuel emissions. The biological feedbacks that both sustained and eventually ended the Great Rains have modern analogs in processes like forest dieback, permafrost melting, and ocean acidification that could either amplify or moderate our own climate changes. Perhaps most importantly, the Carnian Pluvial episode provides a vivid demonstration of how climate changes that might seem gradual and manageable on human timescales can create environmental conditions that fundamentally alter the rules governing life on Earth. 2 million years might seem like an incomprehensibly long time from our human perspective, but in the context of evolutionary and geological processes, it represents a relatively rapid transformation that caught many organisms unprepared and drove massive changes in biodiversity and ecosystem structure. The extinction events that occurred during the Great Rains offer particularly sobering lessons for our modern world, which is currently experiencing what many scientists call the sixth mass extinction, as species disappear at rates that rival those of the great extinction events of the geological past. The Carnian extinctions demonstrate how environmental changes that initially seem beneficial, like the increased water availability that supported massive biological productivity during the early phases of the endless storm, can evolve into conditions that become hostile to the very organisms that initially benefited from them. The toxic anoxic conditions that developed in many aquatic environments during the later phases of the Carnian Pluvial episode provide chilling parallels to the dead zones that are expanding in our modern oceans due to nutrient pollution and warming temperatures. Yet the story of the Great Rains is not merely one of catastrophe and extinction. It is also a profound testament to the resilience and adaptability of life in the face of seemingly impossible challenges. The evolutionary innovations that occurred during the Carnian Pluvial episode, the rise of dinosaurs, the diversification of plant communities, the development of new ecological relationships, demonstrate how periods of extreme environmental stress can also become periods of unprecedented evolutionary creativity. The organisms that survived the Great Rains didn't just endure the changed conditions. They used them as opportunities to explore entirely new ways of being alive. This lesson about the creative potential hidden within environmental crisis may be one of the most important insights that the ancient world can offer to our modern predicament. While the climate changes that we are creating pose serious threats to existing ecosystems and human societies, they also represent opportunities for innovation, adaptation, and the development of new relationships between human civilization and the natural world. The biological communities that emerged from the Great Rains were fundamentally different from those that had preceded them, but they were also more diverse, more resilient, and better adapted to the new environmental realities of their world. The Carnian Pluvial episode also demonstrates the importance of time in understanding environmental change. The Great Rains persisted for 2 million years, a time span that encompasses thousands of human generations and represents more time than has elapsed since the earliest members of our own species first appeared on Earth. This temporal scale reminds us that the environmental changes we are creating today may have consequences that extend far beyond our immediate planning horizons, affecting not just our children and grandchildren, but potentially hundreds of future generations. The geological record preserved from the Great Rains provides a unique window into how Earth systems respond to and recover from extreme environmental perturbations. The chemical signatures preserved in rocks from this period, the fossil evidence of biological innovation and extinction, and the physical evidence of landscape transformation all contribute to our understanding of how complex Earth systems behave under stress. This ancient record serves as a natural laboratory that can inform our predictions about how our own environmental changes might unfold and what kinds of adaptations might be necessary for both human societies and natural ecosystems to thrive under changed conditions. Perhaps most profoundly, the story of the Carnian Pluvial episode challenges us to think about resilience and adaptation on timescales that extend far beyond normal human planning horizons. The organisms that successfully navigated the Great Rains were those that possessed the flexibility to adapt to rapidly changing conditions, the resilience to survive temporary setbacks, and the creativity to exploit new opportunities as they arose. These same qualities, flexibility, resilience, and creativity, may prove to be the most important assets that our own species can cultivate as we face the environmental changes that our industrial activities are creating. The Great Rains remind us that Earth is a dynamic, ever-changing planet, where the only constant is change itself. The stable climate conditions that have characterized human civilization for the past 10,000 years represent just one brief moment in a much longer story of environmental transformation and biological adaptation. Understanding this longer perspective doesn't diminish the significance of current environmental challenges, but it does provide a context that can inform more realistic and effective responses to those challenges. As we contemplate the echoes of the Great Rains in our modern world, we are reminded that we are not the first life forms to face the challenge of surviving on a rapidly changing planet, nor will we be the last. The story of the Carnian Pluvial episode teaches us that while environmental change can be devastating, it can also be transformative in ways that open up entirely new possibilities for life. The question facing our species is not whether we can prevent all environmental change. The geological record makes it clear that such change is inevitable, but whether we can develop the wisdom, flexibility, and creativity necessary to adapt to change in ways that preserve and enhance the richness of life on Earth. The Great Rains ended more than 230 million years ago, but their influence on the trajectory of life continues to this day. Every dinosaur fossil we discover, every bird that flies overhead, every forest ecosystem that captures carbon from the atmosphere carries within it the evolutionary legacy of those 2 million years when water fell from the sky with the persistence of gravity itself. We are all, in some sense, descendants of the Great Rains, inheritors of a world that was fundamentally transformed by an event that demonstrates both the fragility and the resilience of life in the face of environmental extremes. The cosmos may be vast and ancient, but it is also intimately connected to our daily lives through the deep history preserved in every rock, every fossil, and every breath of air. If these stories of deep time have sparked your curiosity about the incredible history of our planet and our place within it, consider subscribing to the Sleepy Cosmos, where we explore the most fascinating chapters of Earth's 4.6 billion year journey from cosmic dust to the vibrant, living world we call home today.